Hello everyone. Hello. Good evening. Can someone confirm that I am audible?
Yes, ma'am.
Yeah. Okay.
Yes,
So welcome to today's class. Thank you for joining. So today will be so this is the second week tutorial. So I'll start the class now. So it is being recorded, just to let you know. Okay. So I have shared my screen. Uh, so welcome to the course on fundamentals of micro and nanofabrication. So this is week 2 tutorial. So today we'll be talking about defects, diffusion and ion implantation. So if you guys have any doubts on these topics, you feel free to ask, or yeah, so if I know the answers I can tell, or I can even ask prof and let you know the answers. So yeah, don't be shy. Okay, so let's start with the problems. So today's first problem, I have taken a problem from the assignment that I had got when I had done this course. So this is a bit long problem, so I have divided it into parts. Right. So so the first part is just telling us the background. So why is this problem important and what we will understand by doing this. So let us read it. So a tale of two metals. The performance of the modern microprocessor is often limited by the conductivity of the metal interconnects. So until 1990s, industry exclusively used aluminium for interconnects. On paper, copper has a higher conductivity than aluminium, but still until 1990s it was never used for IC fabrication. So what they are saying is, even though copper has higher conductivity, uh, we were not able to use it until like 1990s, and we were using aluminium. So the reason that they are saying is, the reason is that when we use copper over silicon, it kills the device performance, and that is due to rapid diffusion of copper in silicon. So this question is about the topic of diffusion, and now we will understand why, quantitatively understand why copper is not preferred. Copper not used to be preferred, and aluminium was the preferred metal for diffusion, for making metal interconnects on silicon. Okay, so we shall investigate why copper was so hard to work with. So right, so in the problem we are given given a few things. So the first is uh, that copper concentration in silicon needs to be less than 10 power 11 per centimeter cube. So what they are saying is, in a centimeter cube volume of silicon, so we have a silicon wafer, right, like just like last time. In the silicon wafer, in some particular volume, we need to have copper atoms lesser than 10 power 11 per 1 centimeter cube of volume. So the device that we want to fabricate, so the device that we want to fabricate it makes this requirement necessary. Okay, so the wafer that we are working with is 500 micrometer thick. This is the cross sectional view, but all the devices, so the active layer is only 10 micrometer. So all the devices will lie in the first 10 micrometer. So on silicon wafer, we deposit 300 nanometer thick layer of copper for metal interconnects. So for making metal connections, we have deposited some copper. Maybe there is some pattern of copper on top of the active layer of silicon. Okay, so this is where the problem comes. So once we have deposited copper on top of silicon, even though we don't want it to diffuse, some part of it will diffuse into the silicon layer. Now the problem gets worse when when for further processing, we require that the wafer is set at 400 degrees Celsius for 15 minutes. So after the copper deposition, the wafer had to go through some more processing. all the further processing required the wafer to be at 400 degrees Celsius for 15 minutes. So this is the problem. They have given us what is the impurity, how much of the impurity has been deposited on top of silicon. Now we have to find out how much of this impurity will diffuse into the silicon at this temperature and for, at this temperature for so much time. And another thing that they have given is the solid solubility of copper in silicon, that is so much. Okay. So first of all we have to decide what approach we are going to use. So if you were to model diffusion of copper into the underlying silicon using Fick's law of diffusion, which formula will be applicable? So they are asking now which formula should we use. So in the class Fick's law of diffusion was taught. So we were taught the first law and the second law, and from that how do we arrive at the equations. So for arriving at the equations, you remember we used two types of boundary conditions. So one was the infinite dopant case and another was the finite dopant case. So in this case, which one should we use? Should we use the infinite dopant case or the finite dopant case? Anyone wants to answer? Hello. You can just take a guess. So in this case, you remember, so we have put copper on top of silicon, and this copper is supposed to make interconnects. So so what will happen if all the copper gets diffused inside the silicon? So there is so the concentration at the top will change, right? But we don't want that to happen. So to ensure that the copper on top remains, intuitively we can guess that okay, so someone is saying finite, Mir, right? Hi Mir, can you tell me why you are saying finite? Hello Mir, can you hear me? Okay. So you think that the copper at the surface, the concentration will change. That is what you mean by finite, right? So if that happens, what will happen is, so that will mean that the entire copper layer, the copper has got diffused inside the silicon. Then we won't be able to make interconnects out of it, right? Okay. So let us just start, instead of thinking qualitatively, let us just start with whatever we are given. So they have given us the solid solubility. So solid solubility is 2 into 10 power 12 of copper in silicon at 400 degrees Celsius. So the solid solubility is given to be uh, 2 into 10 power 12 per centimeter cube. So if this is the solid solubility, what is the total number of copper atoms in the wafer? So what is the, sorry, what I meant is, what is the total number of copper atoms that can diffuse in the wafer? So what does solid solubility mean? So this many number of atoms can at max be diffused in 1 centimeter cube of wafer. So that means that solid, so the total number of possible atoms, total possible copper atoms in entire wafer will be 2 into 10 power 12 into the volume of the wafer, right. So what is the volume of the wafer? It is the area of the wafer, that we do not know, into the thickness. So the thickness we know is 500 micrometer. Okay, so 500 micrometer, I can write it as 10 power minus 4 centimeters. because this is in centimeter cube, I like to keep it in centimeters. So what do we get here? 10 power 11 times area. If you just do 5 2s are 10, and yeah, it will come out something like this. Okay, so this many copper atoms can at max diffuse in the wafer. So now let us find out how many copper atoms are there in the top layer. So how do we find out that? To know that, we should first know the density of copper. So that we can find out on the internet, and I will give it to you now here. So density of copper, I should have given in the question itself, I think. So density of copper is 8.96 gram per centimeter cube. So if this is the density of copper, then what is the total number of copper atoms in the deposited layer? So to find that out, total copper atoms in deposited layer. To find this out, we just simply, so this many per centimeter cube. So this many means 8.96 into Avogadro number per centimeter cube. Then how many in the entire, so this thickness was given, right? The thickness was, I think, 300 nanometers. Let me check. 300 nanometer. So the total copper atoms in the deposited layer will be 8.96 into 300. So 300 nanometers means 10 power minus 7 centimeters into the area is again the same area we have deposited, let us assume, and into Avogadro number. Avogadro number is 6.022 into 10 power 23, I think. So, so this is the number that we want. So that will come out to be something around, I will just write it down, I have done this before. So that will come out to be something around 2.5 into 10 power 18 times area. So these many copper atoms are present in the deposited layer. Now just for comparison, if you look, this is 10 power 11 times area, and this is 10 power 18. So we see that the density of copper, the total number of copper atoms that we have is way higher than the total number of copper atoms that can actually diffuse in the given amount of silicon. So from this, what can we conclude? Should we use the finite assumption or the infinite assumption?
Infinite.
Right. So that's why we should use the, you're right. So we should use infinite. So that's why we'll go ahead with fixed equation for infinite dopants, or rather we can say the dopant concentration at the start for x equal to 0, the dopant concentration remains fixed. Okay. So now we decided which equation to use. The next thing is, if you remember the fixed equation, it was something like, I will write it here. So for the infinite case, the fixed equation was C of x comma t. So this is the concentration as a function of position x is equal to Cs, that is the solid solubility, times error function of x by 2 root dt. So this t is just time. So time we know is 15 minutes. Cs they have given us. So the only parameter that we don't know here, so we say we want to find the C of x comma t. The thing that we don't know is this d. Now in order to find d is what? Diffusivity or diffusion coefficient. So in order to find the diffusion coefficient, we take use of this equation here. So either we can just go on the net and find the diffusion coefficient for a given temperature, but it happens that most of the time it's easier to get the value of d naught. So d naught is nothing but the diffusion for infinite temperature. So okay, so when we plot diffusion versus temperature, right, versus inverse temperature, so when we plot log of diffusion versus inverse temperature, we usually get straight lines, and the intercept of these straight lines at 0, so at 1 by T equal to 0, so that is infinite temperature, is given by D0. So this D0 value we can easily get for all the materials. So for the for copper in silicon, the D0 value is this, and the energy, so the what is it called, the I forgot the name. So someone remembers what was EA called? Uh, Activation energy, right? Thanks. So the activation energy, is given by, for copper diffusion in silicon, is given to be 0.43 electrovolts. So and this is the Boltzmann constant and the temperature that they have given us. So from this, can you find out D at 400 degrees Celsius? This is the equation. So it's just substitution. So D is D naught is 0.0047 times e power minus 0.43 into 1.6 10 power minus 19 upon kT, 1.38. So like you can do it. Finally, I'll just tell the answer. So that is 2.86 into 10 power minus 6 centimeter square per second. So you get the idea, right? So if they have given you D naught and EA, we can easily find out D. So the next task is to find C. So this is our copper, and we want to find what is the profile of copper as it starts diffusing into the silicon. So this part is x equal to 0, and as you go down to x equal to 500 microns. So for the given thermal budget, what is the diffusion length of copper atoms into silicon? So first of all, what is thermal budget? Thermal budget is nothing but the temperature and the time that they give us. So what temperature for how much time? So the concise word to tell that is thermal budget. So for the given thermal budget, that is for temperature equal to 400 degrees Celsius and time equal to 900 seconds, find the diffusion length. Again, diffusion length, so this is just direct formula substitution. We can get it to be this. So from the previous question, we know the diffusion coefficient now, and diffusion coefficient into time gives us the diffusion length. Okay. So till now we have found out root dt, we know Cs. Now from Fick's equation for infinite dopant case, at what depth in silicon will the copper concentration reduce to less than 10 power 11 per centimeter cube? So yeah, I have accidentally already shown the answer, but how will we go about doing this? So they are asking us, so what we expect. So this is copper, this is silicon. So the copper will start to diffuse, and slowly the concentration will go down. Someone is asking something. Can you unmute and ask? Okay, for the
Ma'am, such type of questions will be asked in exam like this sums and all.
in the quizzes, I don't think. Exams, I'm not sure. I have not given the NPTEL course, but these were these were our assignment questions when we did this course in ISC, like in campus. So they can be asked. I don't know.
Because in quizzes there are not such type of questions. There are only theory based questions,
Yeah, yeah. In
which
quizzes, there are
actually
just
these
multiple.
formulas and all that thing is not thought by sir.
These formulas are directly from the slide that I am taking.
Okay.
So he has exactly shown all of these things in slides, just that the numbers I am putting it like were not there. So this formula is done, the fixed equation is taught, also this diffusion length he has told in the class.
Yes.
Okay. Yeah, about the exam I am not sure. Like, I have not taken the NPTEL course before, so. Huh. So yeah, so from fixed equation, at what depth in silicon will the copper concentration reduce to less than 10 power 11? So they have given us C of x comma t. So at what concentration? Uh, so, uh, so we have to find for what x will C of x comma t be less than 10 power 11. So when copper starts to diffuse into silicon, at the interface there will be more concentration, and as we go far, the concentration will go on reducing. So this relationship is given by this equation, and yeah, so this equation like prof has shown a simple like not derivation exactly, like how we get this equation they have shown in the class from the fixed. So there is fixed first law and fixed second law. From that you get a second order differential equation in position and first order in time, and then by applying some boundary conditions you get this solution. So yeah, so so from that's where this equation is coming from, and now we have to find for so for what x we get C of x comma t equal to 10 power 11 per centimeter cube. So everything is given, we just need to substitute again, and we can find x. So here we find that x is equal to 1406 micrometer. Uh, so do you guys want to actually do it, or maybe you can do it at home, right? Like on your own, like it's just substitution. Um, it's okay, right?
Yes, ma'am.
Huh. So right. So then we see that the so the diffusion length is 1406 micrometer. So if you see an average copper atom could have diffused all the way down to 1406 micrometers, but our wafer is only 500 micron thick. So what does that mean? So the copper is all over the wafer now. So the impurity has gone all the way through the wafer. So then that is what is the problem with copper. Copper diffuses very fast. Forget about the first 10 microns, it has already covered the entire wafer. So then the 10 micron of active region is no more useful to us, because we didn't want the copper to go inside. So if you remember, the starting requirement was that the copper concentration should be kept below 10 power 11 per centimeter cube, 10 power 11 atoms per centimeter cube. So yeah,
Excuse me,
yes,
I
yes.
have a doubt. Like in this equation, the error function
Hmm.
of some constant. So how we are going to get that ERFC of any value or
Okay, so you can get the online calculator for that. If you want, I can share you the link, like Mathematica or every. Um, just a minute, I'll.
because X will be unknown. So
Huh? Yeah, yeah, yeah. Error function will be unknown. So in exam, if you are asking, they might give you the required value. Okay, so here you will
okay, okay.
require error function inverse actually, because you want to calculate the x, right?
Inverse. Correct, correct.
Just a minute, I'll find the. I think I have the website. I'll share it to you.
Yeah, yeah, sure.
Try opening this. Is it? You, uh, like just like you find some tan inverse calculator, right? You can also find an error function. So this is not actually error function, it is complementary error function, like ERFC you search for. Okay.
Okay, okay.
Hmm. Okay.
Thank you.
Can you see my screen now? I accidentally started from beginning.
Yeah, yeah, we can see.
Okay, thank you. So that way you can calculate ARF. See, in exam I think they will give, so you don't need to worry. So calculate the dose of copper in the wafer. So yeah, so the dose is nothing but, so the function of concentration versus x looks something like this. So this is basically, so if this is my copper here and this is the silicon, just I am drawing it vertically, then how the copper is getting inside the silicon, that concentration versus x. So x is like how deep it is going inside the silicon. So that is this curve. So area under this curve tells us how much copper has diffused inside the silicon. So the total amount of copper. So that is given by the integral of C of x comma t. Right. So then that is called the dose. So the dose formula for the infinite source case is given to be this. So this also I am picking up directly from his slide. So this formula is there. So using this formula, if they ask you to calculate the dose of the copper in the wafer, you should be able to do it. So again we know the solubility, we know the diffusion coefficient and the time. So one thing to note is, if the diffusion coefficient is higher, then the dose will be higher. If time is higher, so if we are keeping it at a higher temperature for a higher time, then the amount of dopants inside the silicon will increase. Also solid solubility, it's directly related. So now this was for copper, right? Can you all try it for aluminium? I am giving the values here. Uh, here you don't need to find the D. I am already giving the D at 400 degrees Celsius. So it is 1.83 into 10 power minus 23. The solid solubility also I am giving at 400 Celsius. And we want to find the X for which C of x comma t is less than 10 power 11 per centimeter cube. So yeah, time is again say 15 minutes. Yeah, so you can do it. Finally, you will get answer as, or should we do it? We can do it here. So ERFC of x over, Hello. Nothing. Like I was trying to find the error function. Can you see my screen now? Hello. 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 Uh, yeah. So basically, if you find it out, I'm not able to do it right now, but we should get it somewhere around 0.97 nanometers. Okay. Similarly, we can also calculate the dose. So the dose equation is Q of T equal to 2 by root pi Cs root of dt. Okay. So from this we know all the things. We can calculate dose of aluminium. Uh, the expected answer I can tell you right now. Uh, so expected answer is 1.44 into 10 power 8 atoms per centimeter square. So if you compare this with the previous dose that we found, uh, like we did not do the calculation, but here the dose that we are supposed to find is 10 power 11 per centimeter square. If we just substitute in all the things, we will find this. So if you look at this, this is 10 power 11 for copper, whereas for aluminium it comes out to be 10 power 8. So it's significantly lower, 3 or 4 orders of magnitude lower for aluminium. And this is also seen from the diffusion graph of copper and aluminium. So if you look, the 10 power 11 concentration is reached for copper diffusion after 1200. So this I have taken from the net. So our calculations differ slightly from what is there, but the copper concentration, if you look, it goes down. Uh, like uh, like it goes down to 10 power 11 atoms per centimeter cube after 1200 micrometers. But on the other hand, aluminium concentration, this is going down to 10 power 11 only around 8 picometer. So that is the thing. So in aluminium, uh, the aluminium will diffuse very small depth in silicon, and the rest of the silicon will remain almost pure. Okay, so that is why the first 10 micrometer, that was our device layer, it will not have as much aluminium in it when compared to when we put copper on silicon. So that was the idea. So that's why aluminium was preferred earlier for making interconnects, for electronic interconnects. However, now they have found out techniques to prevent this diffusion by putting some intermediate layer or by some other procedures. They are able to reduce the diffusion and also take out the impurities from copper by some methods, which are not taught in the course, so we won't discuss. But yeah, so that was the major reason why aluminum was preferred until 1990s for interconnects. Okay, so now this was the only big problem that I had. Next few we will go through quiz like problems. So these are last year's NPTEL quiz problems. So yeah, so consider the following statements. Interstitial diffusion does not need any vacancies. The activation energy of interstitial diffusion is lower than that of substitutional diffusion. And impurities with comparable size to the bulk diffuse substitutionally and smaller ones diffuse interstitially. Choose the correct option. Uh, yeah, so the first option is interstitial diffusion does not need any vacancies. So is that true? So they have shown a small cartoon of interstitial diffusion. So this is the impurity. So all the silicons are in the respective places and the impurity occupies an interstitial site. So the silicon don't need to move away from their original place. So that's why we do not need any vacancies. So this is true. The second one is the activation energy of interstitial diffusion is lower than that of substitutional diffusion. So is this true? So what is the activation energy? It is the energy required. So for any like if we had learned this in, I think, chemical kinetics in our previous classes. So for any process, the initial system has some energy, final system has some energy, and to go from the initial system to the final system, it has to overcome some additional energy. So this difference is basically called the activation energy. So will this difference be higher? So this is energy, x is just I don't know, reaction coordinate or something like that. So so will this difference be higher for interstitial diffusion or substitutional diffusion? So remember, in interstitial diffusion, we do not need to move the silicon atoms and create a vacancy, whereas in substitutional diffusion we need. So for one impurity to hop from one substitutional site to another substitutional site, there needs to be a vacancy present. So naturally, in this case, the activation energy required will be higher. So the activation energy for interstitial diffusion is lower than that for substitutional diffusion. So this is also true. So the next one is impurities with comparable size to the bulk diffuse substitutionally and smaller ones diffuse interstitially. So yeah, so this is also like quite obvious. This is also true. So if you have an impurity which is bigger in size, it won't be able to go to the interstitial sites. So it will need to substitute some silicon atom. So that is the case. So this is the correct option. So yeah, this is about solvent cleaning. So solvent cleaning just means that we put the sample in a solvent, and whatever impurities dissolve in that solvent will be removed due to the solvent cleaning. So what is the correct sequence of basic solvent cleaning from the following? Someone wants to take a guess? for hint I will give this. So, this is the boiling point, and for different solvents. So, we do not need this, we just focus on these three. Can someone answer please? Sorry, I was not audible, right? Now am I audible?
Yeah, yes,
Okay.
ma'am.
Uh, yeah, I for some reason I lost connection on my laptop. Uh, okay, so from when was I not audible? Okay. So, um, were you guys with me for problem 2? Hello?
Yeah, you were showing about all those findings with aluminium.
Oh, so from
Yeah, yeah, correct.
here. Oh man, okay. Sorry, I didn't check the chat. Okay, so right. So we can do the same thing for aluminum that we did for copper. So we have D solid solubility, and so we have to find out what is the concentration when 10 power 11 atoms per centimeter cube concentration is reached. What is the X for which we get this concentration? So we can do the same analysis, just the same what to say, the same just substituting in the same equation. The equation was C of x comma t is equal to, hello, is my audio still unclear?
No, ma'am, it's clear.
Okay. Huh. So with this, so just by substituting in the equation, so Cs ERFC x by 2 root dt. So just by substituting in this equation, we can get that x should be equal to 0.97 nanometers, and then we can calculate the dose, and the dose that we calculate comes out to be, so I have not done it but here, but we can just substitute and check, it comes out to be some of the order of 10 power 8 atoms per centimeter square. So for aluminium, the dose of aluminium in silicon is 10 power 8, and also the diffusion depth, if you check, uh, so the x for which we get 10 power 11 as our concentration is 0.97. Now if we compare that to copper, in case of copper we had 1406 micrometers depth and 10 power 11 dose, and here we are just having the depth in depth of penetration in nanometers, and the dose is also 10 power 8. So there it was 10 power 11. So there is an order like 3-4 orders of magnitude difference, and that is why aluminium is used for interconnections, because it does not cause as many defects in silicon and it does not diffuse that much in silicon. So, this is just a comparison graph. So, here you see that for copper concentration of 10 per 11, this is achieved at somewhere around 1200 1400 micrometers. However, aluminum concentration of 10 per 11 is achieved somewhere in picometers. So, you can see that aluminum will only, so if this 10 micrometer of silicon was my device layer, aluminum will only penetrate some picometers of it, whereas copper will penetrate throughout. So, the device layer is totally gone. So, that is why they use aluminum for interconnects, they used to use, and now these days they have some other advanced techniques to avoid this problem to some extent, and also sometimes they put some barrier layer in between. So, copper cannot diffuse as efficiently in the barrier layer. So, that helps in avoiding copper diffusion, and there are also other advanced techniques that they use to avoid this. So, so that was about it. So, then I talked about problem 2. So, after this all the questions are just quiz like questions, so multiple choice. So, consider the following statements. So, the first statement is interstitial diffusion does not need any vacancies. So, is it true or false? So, what is interstitial diffusion first of all? So, if this black one is the impurity atom, and so we can see that this impurity atom has gone and sat at a position in between the silicon lattice. So, the silicon lattice has not moved, only the impurity is sitting at the interstitial sites. So, that is interstitial diffusion. If the impurity has to substitute the silicon in its lattice position, then that is the substitutional diffusion. So, then does interstitial diffusion need any vacancies? No, right. So, it anyways just has to sit at the interstitial position, it does not need to displace any silicon. So, it does not need. So, this is true. The second question is the activation energy of interstitial diffusion is lower than that of substitutional diffusion. So, the activation energy basically means that, so if I have a reaction or a process, if this is my the energy of the initial state and energy of the final state, to go from the initial to final state, we need to, so Mir, do you want, you said yes for what? Hello Mir? Mir. Okay, so the activation energy of the interstitial diffusion is lower than that of substitutional diffusion. That means that the energy required for the interstitial diffusion to happen is lesser than that required for substitutional diffusion. Yes, so yeah, so that is true, you are right. Yeah, so this is also true. And so the next one, impurities with comparable size to the bulk diffuse substitutionally and smaller ones diffuse interstitially. So, is this true or false? So, they are saying that impurities with sizes which are comparable to silicon, they will diffuse substitutionally, that is they will move the silicon from its place and occupy the vacancy. So, whenever there is a vacancy, only then it will move, right. So, this is also true, you are right. So, that means A, B, C, all the three are true. So, the next problem we have to tell, so this is about solvent cleaning. So, what is the order of solvent cleaning? So, first we will use acetone or first we will use IPA. So what is the order that we should follow? So for that the hint is given. The hint is the boiling point. So the boiling point of all the solvents is given here. 1, is it? So Nanindrajit, can you tell why 1? Like what is the explanation? So how can you explain it with the help of the boiling point? It is correct. So basically we should always do the solvent cleaning in the order of increasing boiling point. Yeah, if TC is an option, then we can just do this. Like the same logic will apply. Uh, so first 56, then 65, then 74, then 83. At least that is what I believe. So what it means is, so the boiling point basically is telling us how much it will wet the surface. So it might happen that if you just take it out of acetone, it will dry instantly after you take it out. So you won't be able to actually blow dry it. So there will be some watermarks or coffee stains, like this is your wafer. Some amount of acetone might dry here and it will make a stain over there. So we don't want that. So the quality of the wafer will reduce. So quickly after putting in acetone, we will put it in methanol. Then quickly later we will put it in IPA. It also gives us the added benefit that different impurities might dissolve in different solvents. But in addition, it's best to do the IPA wash at the last. So that will ensure that the wafer is wet at the end, and when it is wet, we can easily blow dry it. So there will be no IPA residue left that evaporates from like and leaves a stain. We can blow dry it onto some, so we can keep a wipe and we can blow dry it onto it. So which of the following statements is false? The advantage of OMI clean are room temperature, fewer steps, fewer costly chemicals and lower waste. So OMI clean was discussed in class. So this is an advanced clean suggested by OMI. So the problem with, so yeah, so the original cleaning recipe, so the standard cleaning procedure is given here. So you can see the number of steps in the standard cleaning. In standard cleaning, we have to first do a piranha clean, so just to remove any gross impurities, then rinse it, then put a HF dip to remove the oxide. So whenever we do piranha clean, the top layer will form some oxide on it. You are not able to see, is it? Just a minute, I will zoom in. Now is it visible? So I am talking about the standard cleaning recipe right now. Oh sorry. So in the standard clean, if you see, first we do a piranha clean. So piranha clean will remove any particles or organic impurities. So this is optional. If your wafer is clean, you don't do it. The next process is, because we did a piranha clean, there will be some oxide that is formed on top of it. So we need to remove that. Now to remove that, we do a HF dip. After the oxide is removed and after we rinse it properly, then we do RCA1 clean. So for RCA1, these are the chemicals and the proportions, and that takes 10 minutes, and we also have to ensure that the temperature is 70 degrees Celsius. So to reach at that temperature also takes some time. Then again we do a water rinse, and again we remove the oxide that is formed. Then again we do a RCA2 clean, same process again, remove the oxide, DI water rinse, then spin. So there are so many 10 processes involved in the standard cleaning procedure, right. So the next type is what they are suggesting is OmiClean. So in OmiClean, what they came up with was a simple 5-step procedure. It is not simple, but the number of steps has reduced. So what they do, instead of uh, using H2O2 to oxidize like in Piranha or in RCA1 and RCA2, they use ozone, 5 parts per million of ozone in water to oxidize the impurities, so organic or carbon or metal impurities. So just ozone can help us remove all of these. Then again, to remove oxide we still have to use HF. So but the recipe is different here. But the thing to note here is that all the things are happening at room temperature and there are lesser number of steps. So that is why the advantage of OmiClean are room temperature, fewer steps, and since the steps are lesser, so the cost of chemicals also goes down and lower waste is produced. So this is true. Why I can't write? Okay. So the first one is true. What about the second one? Okay. The disadvantage of wet cleaning are particle contamination from liquid, coffee stains, gallons of expensive chemical waste, and difficulty in hazardous waste disposal. So yeah, this is also true. So whenever we do wet cleaning, we use a lot of chemicals. I think plasma cleaning is considered as a dry cleaning method. Yes, you are right. So that means which one is false? Solvent cleaning, I think the third one is false, right? So this is the answer. So this is false. Right here. So yeah, so we have essentially solved it. So the second one is true. What about the last one? Solvent cleaning removes organic contamination and is compatible with metal coated wafers. So this is also true. So usually with metal coated wafers we can't do Piranha or RCA. So we have to stick to solvent cleaning. So which of the following can be used to detect chemical contamination? So anyone remembers this? This was also discussed in class. So what we can do is we can rule out some of the possibilities. So what about optical microscopy? So in microscope, can we really check for chemical contamination? Option 2, is it? Why do you think so? Yeah, spectroscopy, photo emission spectroscopy. For some reason it doesn't write. Yeah. So yeah, this is actually the correct answer. I am not sure much about photoluminescence and electroluminescence. So basically these are some kind of electrical characterization techniques, but from what sir discussed in class, these are used for particulates. So optical microscopy we can only see particles, or we can even do this dark field microscopy to enhance the contrast, but we cannot differentiate between chemicals, or we cannot see if there is a chemical impurity. Even in SEM on its own we cannot do it, we need to use something called as EDX. So EDX helps us know which, so it is also kind of like spectroscopy, it helps us know which material is there. Photoluminescence and electroluminescence also comes for particulates, and as you said we can do photo emission spectroscopy. Basically just send this is like send light onto the sample and electrons will be coming out. So just like photoelectric effect, but we are using this photoelectric effect to judge which material is there. So yeah, maybe you guys might know more about this. I am not an expert, but I just know the concept, like yeah. So yeah, so basically the emission spectra of the material will tell us which material is there. So we can differentiate also between chemicals using the photoemission spectroscopy. So next is again about diffusion. So infinite source and finite source diffusion are two generic cases often seen in dopant diffusion. So select the correct statement. The surface concentration decreases over time with infinite dopant source. So is this true or false? So we have, I think, already discussed this uh, so the definition of infinite source means that the surface concentration should remain same. So even in the graphs we can see that this is surface concentration upon solid solubility, it remains at 1 whenever the source is infinite, but this is not the case in the case of finite source. So that is the main assumption of infinite dosing. So the surface concentration decreases over time with infinite dopant source is false. Sorry. The maximum surface concentration available for diffusion depends on solid solubility limit. Is this true or false? So this also we discussed when we were doing the first problem. This is true. So the maximum concentration that will go inside the material will be equal to its solid solubility. So solid solubility is basically a property of the dopant material, the substrate, and the temperature. So for that temperature, whatever is the solid solubility, only that many number of atoms will diffuse per volume, per centimeter cube. So the third point is the total amount of dopants diffused per unit area, that is the area under the curve, that is the dose. The dose is the area under the curve, right? So the area under the curve increases with time for a finite source. Is this true or false? Someone wants to answer this? So we can just look at the graph and answer, right? So will the area under the is in the finite source case, is the area under the curve increasing with time? No, right? So whenever as time is increasing, yeah, you're right. As time is increasing, the curve is shifting towards the right. However, the peak is reducing, so the net area will remain the same. And that is because we have a fixed amount of uh, fixed amount of dopant present. So only that much will. So it's not an infinite source. So the total amount of dopant should remain the constant. So the dose will always remain same. Yeah. Thanks, Mir. Okay. So problem 7. So silicon dioxide can be used as a diffusion stop mask to pattern the dope layer. So silicon dioxide can be used as a diffusion stop mask to pattern the dope layer. Diffusivity values of phosphorus and silicon dioxide at 1100 centigrade temperature are given. So these are D of phosphorus in silicon and D of phosphorus in oxide. So these both values are given to us. If the masking layer thickness needs to be greater than 4 times the diffusion length of dopant in silicon dioxide, what should be the mask thickness and diffusion length of phosphorus and silicon? Okay, what are they asking? What should be the mask thickness? So mask thickness they have told should be greater than 4 times the diffusion length. So they want to know what is 4 times the diffusion length of dopant in silicon dioxide. Right. So this part is silicon dioxide, this is silicon, and the dopant is exposed to only some parts of silicon. So for this mask to work, the diffusion length of phosphorus in the mask should be 4 times. So, we can just calculate that. So, if you remember, the diffusion length is given by root d times t, right. So, what will be LD of LD of phosphorus in oxide? That will be given by root of 3.17 into 10 power minus 16 into time. Did they give us time? They gave. So, 30 minute diffusion. 30 minutes means 30 times 60. So, we can calculate this, and then the mass thickness will be 4 times of this. Ten power minus 16. 6 is 18, 3 is so after taking it square root, it will come somewhere around this, and then finally we will get something around 30 nanometer. So, this is the mass thickness. So, 31 nanometer. So, we get the third answer. Also, we can find out L silicon. So, L silicon is nothing but, what had they asked? Diffusion length of phosphorus in silicon for 30 minutes. So, root of D for silicon is 1.37 into 10 power minus 13. So, again this is just formula substitution into 30 minutes means 3 6 is 1800. Like if you just do it, I think we will get 157 nanometers. So, this was fine, right? Basically the same formula for diffusion length, we have used it to see what should be the mass thickness. Now let us do another problem. So, again true or false kind of problem. Consider the following statements based on the plots of diffusion coefficient versus temperature. So, again this is also a plot of, I will zoom in. So, if you see, so this is diffusion coefficient on the y axis and it is a log scale, and on the x axis it is inverse of the temperature. So, 1000 upon T, so it is in Kelvin inverse. So, as I told you previously, these graphs are straight lines because diffusion coefficient follows d equal to d naught e power Ea by kT kind of relationship. So, minus Ea by kT. So, because of that these are straight lines, and this is true for most of the materials, and we can see that for gold and copper the diffusion coefficient is of the order of 10 power minus 6 centimeter square per second, and for boron, phosphorus, arsenic it is somewhere around 10 power 12, 10 power minus 12. So, so it is higher in the case of copper and gold. So, that is what we expect, right. So, because copper, gold, these are all metals, they will occupy the interstitial sites, and interstitial diffusion is faster. So, the rate of diffusion, that is the diffusion coefficient, is higher. Whereas for substitutional impurities like boron, phosphorus, arsenic, for these impurities the diffusion coefficient is lower because they because we need to overcome the barrier of the Ea barrier, right. So, this is the initial, this is final. So, the activation energy will be higher because we want to like for the impurities to move inside the substitutionally, the silicons have to be displaced from their position. So, there needs to be vacancies. So, based on the defects and everything in silicon, the activation energy required for boron phosphorus to diffuse is higher. So, yeah, so diffusion coefficient is measured of how fast an atom or molecule is diffusing inside a media. So, is this true or false? So, by now all of us know that this is true, right. So, diffusion coefficient decreases with increase in temperature. Yeah, thanks Meet. It's true. So, diffusion coefficient decreases with increase in temperature. Is this true? False, right. So, this is false. And the third one is, thank you. So, third one is elements gold and copper diffuse faster than boron and phosphorus at certain temperature. Yes. Okay. So, we are like A and C is the correct answer. Thank you. Let us go forward. So, this is about the channeling effect. So, this is from the ion implantation class. So, just to refresh, so till now we were talking about diffusion. So, it is like we just have a dopant on top. So, if I want to so if I want to dope silicon with something, I will put that material on top and it will diffuse into silicon. But in ion implantation, what will happen is we will have some mask like thing, and then we will bombard the ions on top of the silicon, and these ions will be implanted in the silicon. So, basically it is not a passive process anymore, we are putting the electric field and putting the required atoms into the silicon. So, we will know the exact amount of atoms that we have put. So, this is used when we need to know the exact amount, or we need to be sure of how much impurity or how much doping we want in the silicon, not impurity. So, this is used when we need an exact profile, dopant profile in silicon. So, right. So, that was ion implantation. Basically, there is electric field applied, and because of the electric field there will be ions in the so the ions will be bombarded on the silicon, right. So, now in this implanting dopant on common silicon wafer, implanting dopant on common silicon wafer orientations like these has a problem of channeling, where implanted ions do not see many silicon atoms to collide and travel longer distance than intended. Which values of the following parameters will reduce channeling effect? So, dose should be lower or higher? So, will higher dose cause more channeling or lower dose cause more channeling? So, what will happen in channeling is, basically if you see the silicon surface, so since it is a crystalline solid, so there will be atoms arranged in some nice periodic manner. So, there will be such channels basically which the impurities will see, and they can go through them. So, you can see in this cartoon, this impurity is going through a channel. So, somewhere it will collide, but because there are these open paths, it can avoid a lot of collisions. So, because of that, the profile that we expect for a non-channeling case will look something like in the blue curve, but for the channeling case it will have a tail at the end. So, this tail is something that we did not expect from our calculations. So, that is not desirable. So, when we are doing an ion implantation, we want a profile that so the profile to match exactly our expectations, because that is why we are doing ion implantation. Otherwise, we could have stick to doping or some other passive way. Already we are harming the wafer by bombarding it with ions, and if we are still not getting the profile that we want, it is not a desirable thing. So, we need to avoid this channeling. So, how to avoid it? So, should the dose So the dose is how many ion we are bombarding, so how much doping we are giving. So should the dose be higher or lower? Anyone wants to take guess? So what happens is, uh, so to avoid channeling, we need to break the channels. Now to break the channels, it is easier when there is higher dose. So what happens when there is higher dose? The dopant atoms will bombard on the silicon and they will break some of the bonds, and these broken bonds will fall out of lattice, and because of that this exact perfect lattice matched property will be reduced, and because of that the channeling that the new impurity will see. So one impurity knocked out one silicon atom from its place, because of which the lattice is disturbed. Now the next impurity, it will see a disturbed lattice now. So because of that there will be more resistance. So because of that, in the case of higher dopant concentration, so higher dose, we see that the channeling effect is reduced. So uh, so maybe if we saw a profile like this for a lower dopant concentration, in case of higher dope we will see something like this. So even though there will be some amount of channeling, but it will get reduced because the crystallinity of silicon will reduce because of the higher dose. So 10 power 15. So either this or this. So the next option is, should we tilt the wafer or keep the wafer straight? So now when I am putting ions, should I put it on the flat surface or should I put it on the tilted surface? Um, Tilt, right, thanks. So yeah, so for the same reason, so now if the ions are seeing a nice lattice, but when I tilt it, they will not see this lattice, and so the channeling will be reduced. So the atoms that they see will be more crowded, so just by a small tilt, and because of that the channeling will be reduced. So this is the correct answer. So the last question for today, for the same implantation energy, sorry, for the same implantation energy, which ion will have higher penetration depth and higher spread, that is straggle? So how does the implantation energy affect the penetration depth? So just by intuition, what do you think? So if the no, sorry, we are keeping the implantation energy constant, right? Okay, so if the energy is same, the velocity of the lighter atom, so the yeah, thanks, heavy and heavy, is it? So for the same implantation energy, which ion will have higher penetration depth and higher straggle? Um, okay, so another answer is heavy and light. So first of all, let us think about higher penetration depth. Will the lighter atom penetrate more or the heavier atom penetrate more?
Lighter.
Lighter, right? So the first one should be lighter, right? Because the lighter atom will, it will be easier for it to make its way through the silicon. For the same energy, it will also have a higher velocity because it is lighter. So for the same energy, the velocity of the lighter atom will be more, so it will penetrate more. So the first option has to be light, so either this or this. So what about the straggle? Um, so what happens is, the straggle is lower for uh, lower for a heavier atom. So if you just look at this graph, mm, these both are the same, right? Okay, I don't know why. Okay, so for a heavier atom, the spread will be lower because um, okay, I don't know because, but it will be lower. So the correct answer is light and light. Uh, mm, it's like I don't know the technical explanation, but it's something like in the heavier case we can predict it like it will stick closer to the predicted depth, and that is because in the lighter case it will it is easier for it to penetrate even more. So I don't know, I actually don't know the explanation, but even we see the higher spread in case of lighter atoms itself. So light and light is the correct. I think the higher ion will collide more and spread more. Um, Actually, no. The relation that sir told in class is that the heavier ion will actually spread less, have a smaller stagger, and also penetrate less compared to the lighter atom, which will go like more to more depths, and also the spread will also be high. The reason I am not sure. You can check the you can check the presentation. Uh, okay, the reason I'll look up and tell in the next class. Okay, so any doubts for today's class? Also, do you have any suggestions for next class? Like, do you want more quiz type of problems or more explanation based problems or anything like that?
Like more of numerical type of problems may be helpful. Like today, the first problem was good. Like we
Okay,
could understand much better
yeah,
through
sure.
numerical or any practical based, like practical based problems, something.
Sure, thank you. Like, okay, I used to think that that might be too heavy because most of the quizzes problems are like not numerical based, but sure, we can do more of those. Yeah,
Yeah,
thank
thank
you.
you.
Thank you, Arshi. Okay, then we can close today's class. Uh, I'll see you guys on Tuesday. So, thank you.
Thank
Thank you,
you.
ma'am.